today we are going to do section 6.8, which is exponential growth and decay. Now this exponential growth and decay is already covered in algebra. And this section, for some reason your book decided to repeat it here. I'm not sure why. There is nothing new here, with one exception that we'll come to quickly. Now, exponential growth and decay, I would like to remind you, is that model, okay, with the exponent. Look down in the page 734 a little bit. You see the equation where y equals to y0 times e to the power kt, and that is the formula that you plug in stuff. Okay, k is the constant called the growth constant, and y0 is the initial amount, and t is of course time, and that's about it. So if you don't remember that, or if you do, it might not hurt to redo the homework. I just do all the examples of this section. So the homework for this section is just to do all the examples, 4.2 to whatever. I didn't even write this down. I did write it down. It just says all examples. All right. However, there is one thing on the following page that is worth mentioning. That is, this is also developed earlier, with both in algebra or something, and also in chapter 1 when we first mentioned it. In chapter 1, we mentioned this fact. Okay, during the review. That's how I know that you've had it before, because it was in this whole thing is in review. But anyway, in chapter 1, it developed this particular equation, okay? And that's the only part that you didn't know about this section that you didn't know back in algebra. That is, E is the limit of 1 plus 1 over m to the power m as m approaches infinity. Now, we did do this, okay, previously. This might look familiar, but we will, in case you have forgotten, I have wrote it down again just to remind you why that is the case. That's the only thing that you didn't know of this section back in the day. Now, how do you prove this thing? Well, as you can see, 1 over m is m as m goes to infinity. 1 over m is going to 0, right? And then it raised to some power that's going to infinity, so it's kind of like 0 is being raised to infinity, and what is that? And the way you solve this problem is is use the natural log. So we have done this before, okay? And where do we do this? In the famous L'Hopital's rule, okay? The students' favorite. By the L'Hopital's rule, what you do is you let y equal to that whole thing, and then take the natural log of y. Once you take the natural log, I can't read this. Oh, never mind. It says that says, if you can see it, I put it a little closer. Okay, that means you can take the m down from the exponent, okay, and put it in front. It becomes m times natural log of all that stuff, and that's still not good enough, because at that point, you still have m is going to infinity, and then the other thing is going to 0 or something. Infinity times 0 is not getting you anywhere. So you pull off one more trick, is you beat the m to the bottom of the division line. Okay, it becomes 1 over m if you stick it down there, right? You push it down there to become 1 over m. So now you have a 0 over 0 situation of the L'Hopital's rule, which means you're allowed to now apply the L'Hopital's rule and take the derivative. And once you take the derivative, then all kinds of stuff get canceled out, and things go to 0, and then at the end you get 1. Which means what? And then, oh, that's not over yet. Okay, one more line. So once you get 1, then, so the limit goes to 1, which means y itself then goes to e. Okay, e to the power 1 is e. So you get it back, and that's how we prove this equation, which is kind of a neat thing. That's why I go over it again, even though we have done it in the past in the L'Hopital's rule section. So that marks, well, I'll keep talking. So next, now that that's done, that's the only thing that's actually worth mentioning. Next, example 6.4 For 3 compound interest, you plug the proper information into the proper spot, and then out pops the answer. Even the book says so. Okay, you just and there's, as you notice, nothing calculus about it. It's all algebra. Next, doubling time. Another formula that you might have forgotten. If you have forgotten, just take a look at that formula. And then plug it in when you're asked what is the doubling time. The doubling time is natural log 2 over k. And yeah, we don't care why that is. That was developed at one point. And we're at this point, we just need to look at the formula and plug it in. And then, so after exponential growth, we look at exponential decay, which means nothing. You know, the growth and decay, as far as we are concerned as math students, is they're the same. It's just one's positive, one the k is positive, and one the k is negative. That's all. Otherwise, everything will plug in the same way as we always do. And then, well, there's an example of Newton's law of cooling. Example 6.45. Well, plug it in. Okay. That's done in physics, but we're not interested in physics right now. We're just interested in the formula and how we're going to plug it in. You know, we're the math students. We only care about the numbers, not the rationale. And then finally, the another half-life. Didn't we just say that? I don't care. Okay, there's that formula is being repeated, so you plug it in again. What was it called before? I'm not interested what it's called before. Just something like this. And then radioactive dating, yeah, plug it in. And then we are done with this section. But at this point, I want to talk about something that we missed or skipped from the very beginning. That is, let's see, give me a second here. Let me find it. I should mention that the exponential growth and decay is just, that's all there is to it. You're not going to need it the rest of the calculus in the future calculus class that I know of. I mean, the only those couple of formulas is all you're ever going to see. So I'm not sure why the book thinks that is important to put it here. But, well, okay, you know, if the book wants it, then we will do it. So now let's go back. Now we have approached to the end of this class. Isn't that awesome? We made it all the way to the end. I mean, when I started this class, I didn't know if I could make it to the end. I mean, it's just a hobby. You know how hobbies are. We do it for a while and might just give up halfway and pass out like the hair. You know, that I talk about in the beginning of the class. You go along, then something distracted you or something, and then you give up. But I'm very proud of myself and of you to have made it. Wow, we're at the end. How exciting, right? So, at the time when I started this class, there were a couple of topics that I said that we will not talk about it at the time, but we will talk about it at the end of the class. The reason is because they are sort of like rabbit trails, and they're interesting enough to mention, but they're not really relevant or matter to the content at the time. So we didn't want to, take off on the rabbit trail instead of continuing on our path of getting through Calculus 1. But now that we have successfully made it all the way here, let's go back and finish that thing that I said I want to do. And this is on page 171. 171? Oh, okay. 171, which is has something to do with the squeeze theorem. Okay, and after we proved the squeeze theorem, your book started talking about a bunch of stuff that is, like I said, sort of a rabbit's trail, but it was also sort of important if we were to prove it instead of just, take it for granted and wait for it to prove later. Well, when you look at this, what is limit as theta goes to 0 of sine theta? Well, you know what that is, and that is just 0. However, your book at this point didn't know that yet, or at least your book didn't think it did. So how are we going to prove that? Okay, we want to prove that the limit of look at the bottom of page 171, where we're trying to prove that the limit, first, yeah, the limit of sine theta as theta goes to 0 is equal to 0. And we'll prove it the way that your book outlines. Okay, but that's not the only thing we're proving here. There's something else that we need to prove that is even more interesting. So to prove this thing, and remember, now we're relaxing and looking at some of the, past scenery because we have come to the end. There's just one more short section, and that's actually the end of this thing. Proof limit. All right. So now to prove this thing, the way your book did it is that we are going to draw the unit circle, and then there is some theta. Okay, being that we're proving that there's theta, and this is part of the unit circle. The unit circle is a circle whose radius is 1. So it's 1 here, and it's of course also 1 here. And then we're going to drop down, in order to prove this thing, we'll drop down a perpendicular line. And this line is, the length of this line is sine of theta. So the length is sine theta, okay, sine theta. And the reason is because sine theta over 1 equals to sine theta, right? That's how you know that. And then the length of this curve, the length we're talking about, is theta. There's the reason for that. That's the definition of radian, actually, or something. is the length divided by 1 is the definition of the angle. Okay, so this is also theta. If that's not familiar with you, please just recheck the definition of the radian if you've forgotten that part. So that's so far so good. But what your book then says that it is obvious that sine theta is less than theta. Okay, well, it'd be by staring at it. Now, I claim, to me, it is not obvious at all. Which part of it is obvious? You don't know that. Sure, it might look that way, but in geometry, just because something looks that way doesn't make it true. So I want to actually prove that sine theta is less than theta. And to prove that is, I draw another third line here, and this length I will call it A. Okay. And as you can see that, now how do I know this is, what is that? Okay, and my argument is going to be that sine theta is less than A and A is less than theta. And here's how it argues. First, sine theta is of course bigger than 0 if theta is bigger than 0. Okay, and then how do I know sine theta is less than A? Because that's by the Pythagoras theorem. Sine theta is just when sine theta squared plus something else equals to A, then sine theta has to be less than A. Or put it another way, in a right angle triangle, either side is shorter than the hypotenuse. Okay, so that's how I know that this is less than A. And then I argue that A is less than theta. That is, this length, which is called the sector for the circle, okay, the sector is going to be less than the arc, is what this is called. Theta is the arc, this is the sector, and there's a part of geometry that says the sector from the same point is going to be shorter than the arc. Well, the argument, of course, is because the distance between 2 points, the shortest distance between 2 points is the straight line, which is A. And that is actually an axiom, I believe, in geometry. So that's how we know that this is less than theta. So at this point, you look at it and you might think, okay, that is maybe not as obvious as the book says, but still looks fairly obvious, right? And you can see it fairly quickly if you remember what each thing is. However, here's something that is not near as easy. Now, the next step, however, is not near as obvious, which the book also think is obvious, but I want to prove it. But before we do that, because the sine theta as theta goes to 0 is equal to 0. Oh, I didn't finish my sentence. In fact, being this inequality is true, then when we let theta go to 0, okay, then then sine theta has to go to 0 too, because it's less than theta and bigger than 0. So by the squeeze theorem, so you got pushed right in there. It has nowhere to go. It has to go to 0, which is okay. And then as a result, then cosine theta, the limit of cosine theta then becomes 1, because theta goes to 0 will be equal to 1, and that's because the Pythagoras theorem. When you plug in the cosine theta is the square root of 1 minus sine theta squared. So when sine theta goes to 0, then cosine goes to 1. Once that's established. And okay, so that part is pretty obvious, but the second part is, I think, far less obvious. In fact, I couldn't even think of how to do it. And at first, that is, the second part, which is what we're trying to prove here, is that the limit as theta goes to 0, sine theta over theta equal to 1. Now, we have gone through this particular thing several times and proved it in various ways. The fastest way that we can prove right now, being that it's a 0 divided by 0 situation, we use the L'Hopital's rule, and it kicks right out, right? You don't even have to write it down. You can do the L'Hopital's rule in your head. But at that point, back when we were at page 171, the good old days, when we were wondering if we can even make it. So now we look back with satisfaction and pride, right? And look at this thing. And so back then, we didn't know L'Hopital's rule or whatever else that we were doing. And how is this supposed to be proved? And that here's where your book did. Okay, and we're going to do something similar, but we're going to actually prove it rather than just say it's obvious. Now, and so we're going to redraw this picture again, slightly differently, and like this. We'll draw so here's theta, okay, and here's the unit circle that goes down. This is 1, being that it's unit circle. We'll draw basically the same thing, and then here's the perpendicular line, which makes this sine theta just like the previous picture, and then and of course the arc, which is called arc, is not a curve, it's an arc, and at least I think it is. Anyway, so that's still theta, but now your book wants you to draw another line, a perpendicular line from this point straight up, okay? And that this line, if you do the math, being that this is theta, this line over this point, okay, opposite divided the adjacent is what? Tangent theta. So this thing is tangent theta by the definition of theta. And then your book says, from the looks of that, it is obvious that that sine theta is less than theta, which we did mention earlier, which is less than tangent theta. Okay, by the looks of it, that is true. But as I mentioned in geometry, what appears to be true need not be. Okay, you have to actually prove it beyond a reasonable doubt. And that's what we're gonna do. But first, I want to read out how did your book puts it? I want to say, we see that is what your book says. Okay, which I think is funny. Okay, your book says, and we see that. Look at the bottom of the next page. Okay, where it says, we see that sine theta is less than theta less than tangent theta. This is the main reason I didn't finish this part when we were doing this, or I don't think I even covered it, because I want to prove this to be true. Okay, because I don't think anybody can see it. Except looking at it, it seems reasonable. But on the other hand, this is one side, that's the other side. It's not a red. I mean, who's to say that sometimes the theta might be the same as tangent theta or less? I mean, it's possible, right? I mean, you don't know for sure. This is just drawn in such a way that it looks that way. However, it is true, and we are going to prove it. So if you were going to prove it, how would you prove it? Okay, I need you to prove that there's a curve going this way, right? And this is a right angle that goes straight up, and then and everything's related by theta. How would you prove that theta is less than tangent theta? If I say it's not obvious to me, now prove it. And so I stared at it, and off the top of my head, I couldn't think of it. So then I asked the AI, how do you prove theta is less than tangent theta? And then the AI gave me an idea, which then once you get the idea, of course, geometry becomes obvious. What you do is, let me pull out my notes, is you calculate the area. That's the trick. You actually calculate the area of these things. Okay. Now, what we're going to calculate is first the area of this thing, a slice of pie. A slice of pie is called a sector in math, and then or geometry or something, or trigonometry. This is the slice, the pie-shaped thing is called a sector, and then the rest is a triangle. And we're going to show that the sector, which is completely inside the triangle, will have less area than the triangle that involves the tangent theta. So here's how we prove it. First, let's talk about the sector. Right. The sector is, let's name our stuff. Okay. So the O for origin, A for this point here, right? C for this point here, just like in geometry. I mean, don't you love geometry? Those were the good old days. And then B is this point here where x equal to 1. Okay, so we labeled our triangle, and then we are going to, so first I'll calculate the area of the sector. The sector will be called ABO. Our sector ABO. Okay, and now, and this is the sector. I'll draw that thing there to show that that's what that is, which equals to the area of a sector is called is pi r squared, pi times 1 squared. That's, and then times theta over 2 pi, because the whole thing is 2 pi. So if you only have theta, then you have a fraction of that much, which is, of course, when you're all done, that equals to theta over 2. That's the sector area. And then the area of the entire triangle, that would be CBO. All right. So then CBO, which is a triangle. Okay. You see the difference between that and that? Well, doesn't matter. And that should be clear now. So area of triangle CBO is equal to base times height. The base is 1. Okay, this is 1, right? And height is tangent, so equal to base times height over 2. All right, so the argument is, being that the sector is completely enclosed in the triangle, okay, which means this area is less than this area. So the theta over 2 is less than tangent theta over 2. And therefore, theta is less than tangent theta. And that's what we were trying to prove. And that your book says is obvious. Well, this is not obvious to me. And so, but we are done with it. And now we are ready to prove this thing. Okay? As what your book says. Well, we're ready to prove it if I can find where did it go. Oh, right here. Okay, so then from previously, we have proved that theta is bigger than sine theta. So we write this down. This is from previous information. Theta is what? Who's bigger than what? Oh yeah, bigger than, okay, this is just bigger than 0. So, and then that from this point, you notice that theta is less than tangent theta. So we can finally write this down. And then what? Now we're going to pull a trick to make everything come out, which is, in this case, we're going to divide everything. Where's 1? Okay. Give me a second. I don't have 1 here. Okay, found the 1. So then we're going to divide everything in this equation by sine theta. And everything is positive here, okay, because our theta is just a regular angle in the first quadrant for simplicity. So we'll divide sine theta by everything, and then we get a different inequality that says 1 is less than theta over sine theta, and then less than 1 over cosine theta. All right. And now we're getting close. Now we're going to flip everything upside down, okay? Just divided. So if you flip everything upside down in a fraction, the inequality sign has to change, reverse. So then this becomes sine theta over theta, right? My marker is losing its life. Okay. And then, which is bigger than, this is 1 over cosine, this cosine. Now we have come to the end of this equation because earlier, right here, we said that as theta equals to 1, cosine theta is 1, approaches 1. So we'll let theta goes to 1 in this inequality. And using the squeeze theorem, there's 1 here, right? And cosine theta is also going to 1, which means the sine theta is being squeezed into 1. And that concludes the proof. By the squeeze theorem, therefore, this situation holds. And I believe that's the end of what I want to say there. So that is fairly a long and lengthy, strenuous way of proving something that the L'Hopital's, you can see it with the L'Hopital's rule by, just looking at it. But it's still fun because for one thing, you have learned how to use this trick. Then normally, how would you prove that? Well, you don't until somebody tells you, or you realize that you can't. If it's not obvious why that length is shorter, you can compare the area, and it comes out. And I think that's a neat trick. Okay. So at this point, you have an optional homework to do the student project. We're on page 175. Being that there's not much homework in this section, you might as well do that one. It's just for fun, and is to derive the formula of the area of the circle is pi r squared. So after I erase the board, I will talk about it. So please try to do that if you can. It shouldn't be that tough. Well, I don't know. Just try to do that. Okay, that is deriving, reinvent the wheel and figure out why the area is equal to pi r squared. Now, so for the student project that I want you to do for the fun of it, you don't have to. It's more like an optional homework. I should type in optional in here. But the fun part is to rediscover the formula of the area of a circle without knowing any of the stuff, or nearly none of the stuff that we know right now, except for what we just proved. That is this. The limit of sine theta over theta equals to 1. So what we are talking about here is how the great Greek mathematician Archimedes discovered the area of the circle, the formula for it, and he used a method that's similar to the limit concept, even though he never went so far as to develop the concept of the limits. But it's still very, very cool. As you might remember, Archimedes is, I believe, the mathematician who jumped in the water in order to and realize that the water rises, which displaces the volume of his body, and which normally cannot be calculated because it's too weird, right? So then, and then as a result, he was able to prove that the king's goldsmith or something who made his crown has added other objects and saved some of the gold. So I'm sure that guy got executed. But we all know the story of how Archimedes was so happy that he ran out into the street screaming in happiness and naked and stuff. So I hope that's not true. Maybe that's just a silly legend. But it does make a fun read when I was a kid. Anyway, but of course, don't ever try to do that. It's just fun. Doesn't mean you should imitate that part. But anyway, so let's imitate Archimedes in doing this stuff according to the book. To do it, then first we have a graph here. I'm not going to draw it because it's more complicated. See, here is our graph. The only difference is the way I did it, I let theta equal to half of it, just part of the triangle. So then the solution then becomes 2 theta times n equals to 2 pi, where n is the number of triangles. Yeah, is 2 pi, and n equals to then theta over pi. Then what I did is I calculate the area of each triangle, base times height over 2, and then I came up with some formula. Okay, when you're all said and done, the area is equal to pi r squared times a bunch of theta stuff. And being that sine theta over theta is 1 and cosine theta it also goes to 1 as theta goes to 0 because your triangles are increasing, then you derive the area equals to pi r squared. And remember, the way I did it, I happen to I interpret theta as just half of that angle. Your book interpreted it as the whole angle, so they use the double angle formula on the sine, but the result is identical. Okay, the difference isn't large, so you can do it either way. You'll come up with the right answer. Right, that marks the end of this section.